Hey everyone, in this video we're going to talk about section 5.5a, which is about verbal differential equations and verifying solutions. So as a reminder, a differential equation is an equation that relates one or more unknown functions and their derivatives together. There's different ways that we're going to signify seeing a differential equation. So one way is y prime. A differential equation itself is a derivative function. Okay, we can see this with something like dy dx. Or we can also see it kind of like as dx dt. Okay, so it's differential equations are going to be helpful to us because they're going to describe how different quantities change in relationship to other. To me, that almost reminds me a little bit of related rates. So related rates are going to kind of fit in with this if we're thinking about those, rate equations as being differential equations. Something's changing in relation to something else. So for instance, differential equations can describe maybe how populations change, how heat moves, how springs vibrate, how radioactive material decays, and much more. So the first part of this video, we're going to talk about how to identify differential equations from verbal statements. So we're going to look for words that signify some sort of derivative, okay? And so we can see that with rate, okay? That could be like the word increase or decrease. And we can also see it with particle motion terms. So position, velocity, acceleration, all of those are related together by some sort of derivative. So before we get into that though, we need to talk about different types of variation. So we have direct and inverse variation. So directly proportional or direct variation means that as one amount increases, the other amount is going to increase at the same rate. So this equation y equals kx is going to represent direct proportionality. So k in this case is going to represent the constant of proportionality. So this says that the constant of proportionality will be multiplied by the expression that models the relationships described. So a little bit, it kind of looks linear, right? As x increases, it multiplies some sort of value, and that's going to make y increase. Okay, so if we increase x again, it's going to increase y by the same amount, okay? I kind of like to think about this like directly proportional as like hourly wages. Okay, if I work for some sort of hour and let's say that I don't know how much I make, but if I work for 2 hours, I'm going to get paid some sort of constant of proportionality, some sort of hourly wage, and that's going to tell me how much money I make. Okay, so hours times the amount I get paid or my constant of proportionality will give me my wages. Inversely proportional means that as one amount decreases, the other amount increases at the same rate, okay? So this equation is going to be in the form of y equals k over x. The constant of proportionality will be divided by the expression that models as the relationships describes. So I kind of think about that in terms of like speed and time. So like the faster you travel, the faster your speed is, the less time it's going to take for you to get to your destination. So in example 1, we're going to be setting up direct proportionality or inverse, I can't say this correctly, directly proportional statements or inversely proportional statements. There we go. Okay, so the first one says Newton's law of cooling states that the rate of cooling an object is proportional to the temperature difference between the object and the surrounding media. A bottle of water is placed into a freezer that is set at 5 degrees Fahrenheit. After t minutes have passed, what is an equation that can model this situation using W for the temperature of the water bottle? Okay, so Newton's law of cooling is something that we've learned about in pre-calc before when we were talking about exponential equations. There's a couple words that we're going to go through and we're going to underline. So first, I see the word rate. So Newton's law of cooling states that the rate of cooling an object is proportional to the temperature difference between the object and the surrounding medium. Okay? So there's some sort of bottle of water that is placed into a freezer that is at 5 degrees Fahrenheit. Okay? So after t minutes has passed, what's the equation? So W is going to stand for the temperature of the water bottle. And so since we're writing a differential equation, I know that we're talking about the rate of this water bottle temperature changing as time changes. So I'm going to write dW over dt. This is the change in the water bottle temperature over some sort of amount of time. So first, it tells me that it's proportional to something else. So even though it doesn't say directly proportional or inversely proportional, we're going to assume that it means direct. Okay, so if it doesn't say inversely, it just says proportional, the default is going to be direct. So I know that this rate of change, this differential equation, is going to be equal to k, some sort of constant of proportionality, and then that's going to be times the object and then the air of whatever it's around. So we know that the object in this case is the temperature of the water bottle, or the water bottle, okay? And then the surrounding medium is the air, and we know that the air is 5 degrees Fahrenheit. So our differential equation relates the change of the water bottle's temperature with the water bottle, like the water bottle's temperature, the surrounding air, and then that constant of proportionality. So a couple of things just to note here. The denominator says dt, but notice that our differential equation itself's variable is w. So it's not always exactly going to match here, since this is a t and this is a w. That's just something to be aware of. We want to make sure that we're really paying attention to what the variables are, so that way we're setting it up correctly. Okay. The second one says the position of an object moving in a straight line is given by x of t, where t is measured in seconds. During the first 45 seconds of motion, the acceleration of the object is inversely proportional to the square of time. What is the equation that could model this situation using k as the constant of proportionality? All right, so a couple of things. So reading through this, I don't see anywhere where it talks about a rate. Okay, we're missing the word rate. But we can infer that there's going to be some sort of rate implied because of the nature of the words. So first of all, we're talking about the position of an object, and then later on we're talking about the acceleration. So I know that to go from position to acceleration, I have to take derivatives. So that's where that rate is coming into play, using those particle motion terms. Okay, so my position is given by x of t. Okay, my first derivative of that would be the velocity. And the second derivative of that is going to be the acceleration. Okay, so it tells us that the acceleration of the object is inversely proportional to the square of time. So first, let's focus on the inversely proportional part. So I know that I'm going to write this as k over, and the square of time will be time squared. Now, one thing that we need to keep in mind is we need to write this in terms of like how a differential equation is going to look like. So I don't want to use a of t, because even though we know and we've seen before that a represents the acceleration, we always want to try to relate it back to the variables that we were given. Okay, we were given x of t. Okay, so there's a couple different ways that we can write this. I could write this as x double prime of t equals, okay? The other way, a lot of times that we're going to see differential equations being written is we're going to see it written as like dw over dt. So in this case, since we're talking about the second derivative of x with respect to time, I will probably see this and write this as d squared x over dt squared. Okay, these mean the same thing, but I feel like the most appropriate differential equations notation is using the one that I've circled. Okay. Okay, the last one that we have, we're actually going to go through and we're going to solve for k. So in both of the examples above, all we had to do is we had to set up what the equation was, and we didn't actually have to find what that constant of proportionality is. And we weren't able to do that because we weren't given enough information. Let me go back and say that for B, we were told something about 45 seconds of motion. That's going to be the domain of this. That doesn't apply at all to what the equation is. That just tells us over what interval that equation is. I lost my train of thought. Over the interval of over, like, that it's accessible over. Okay, applicable over. Okay, so as I was saying, we haven't found what k was in the other ones, and usually I feel like if this was on the AP test, these are going to show up in multiple choice questions. However, with C, we actually will go ahead and we will solve for that value of k. So C says the volume of a liquid in a tank is given by a differentiable function v, where v of t is measured in liters and t is measured in hours. The volume increases with respect to time at a rate that is directly proportional to the product of time and volume. Then it gives us some information. So at t equals 5 hours, the volume is 100 liters and it is increasing at a rate of 2 liters per hour. What's an equation that could model this situation? So this one infers to us that we're going to find K because it tells us specifics that we can plug into. It's almost like a related rates question. We're given information, we have to solve for something. So let's set up our differential equation. So we're talking about V of t being the volume. We know that the volume increases, so there's that wording that's going to mean that we're talking about a differential equation with respect to time. So I'm going to have a dv over dt. Okay, that's directly proportional. So now it's going to be k times something. And it says it's going to be equal to the product of time and volume. So that'll be t times v. Okay, now that we have all of this, since we have this other information, I'm going to go ahead and plug it in to solve k. So we know that at t equals 5 hours, okay, so t is 5, the volume is 100 liters, and then we know that it's increasing at a rate of 2 liters per hour. So this represents our dv dt. So solving for k, I can multiply my 5 and 100, so that's k times 500. Dividing by k is going to give me that k is equal to 1 over 250. So my differential equation is going to be dv dt equal to 1 over 250 times t times v. All right, when you're ready, we're going to go ahead and we're going to flip over our page and we're going to look at another subset of differential equation questions. Okay, so this subset of questions are going to talk about using derivatives to verify that a function is a solution to a differential equation. Okay, so the solution to a differential equation is going to be a function that satisfies the differential equation when f and its derivatives are substituted into the equation. So whenever it says that we need to verify something, that means that we need to show the truth. Okay, so we just need to use our knowledge of derivatives and substitution to make sure that like one side of the equation equals the other. Okay, really this actually just becomes more of an algebra problem than a calculus problem. Okay, so in example 2, we're going to verify that y equal to e to the negative 4x plus 2x plus 3 is a solution to the differential equation y prime plus 4y minus 8x is equal to 14. So first, I know that this equation here is a differential equation because of this y prime. Okay, so really we're going to take this equation that I've underlined in red and I'm going to plug in y prime and what y is, and then we're just going to combine all our like terms. So I have what y is, but it also says that I'm going to need it to find a y prime. So finding y prime is really just taking the derivative of this. So y prime will be equal to, okay, taking the derivative of e to the 4x, that's going to be the chain rule. So e to the negative 4x times the derivative of negative 4x, which is negative 4. The derivative of 2x is 2, and the derivative of 3 is 0. So that y prime is equal to negative 4 e to the negative 4x plus 2. So I'm just going to substitute y prime and y into this equation, and then let's combine our like terms. So I will have negative 4 e to the negative 4x plus 2 plus 4 times, okay, I'm going to plug in what y is equal to, e to the negative 4x plus 2x plus 3. Okay, I'm going to subtract 8x. Now, here's the deal. We don't have anything to plug in for x, so x is our variable. And that's a good news because look at all the other variables that we have so far in this. All of them are x's. Okay, and so we're going to check to make sure that this is equal to 14. All right, time to algebra it up. Combining our like terms, I'm going to distribute this through. So I'm going to have negative 4 e to the negative 4x plus 2 plus 4 e to the negative 4x plus 8x plus 12 minus 8x. And we're checking to make sure this is equal to 14. All right, I see my my e terms will cancel. They'll add to 0. My x terms will add to 0, and so I'm left with 2 plus 12. and I'm checking to see if this is equal to 14, and it sure is. 14 is equal to 14. So we would say that this equation is a solution to the differential equation because it does satisfy this equation. So I know what you're probably thinking. That seemed pointless. Well, there can be multiple solutions to a differential equation depending on what our functions are. That's what we're going to see in example 3. Okay, so this is more of a multiple choice question. It says, of the following, which are solutions to the differential equation y double prime minus 9y equals 0? So there could be multiple functions that actually satisfy this. So we're going to go ahead and we're going to figure out which ones will. So probably want to write small for this if you haven't already. So for A, I know here that I'm going to need a y double prime. So for our first function, for cosine of 3x, looks like we need to find its second derivative. So we're starting with y, which is equal to 4 cosine of 3x. Okay, y prime would be equal to its derivative. So this would be negative 12 sine of 3x if we chain rule it. And then y double prime will be equal to negative 36 cosine of 3x. So plugging all of this into the differential equation, we're going to see if this satisfies it to make it a solution. So y double prime is negative 36 cosine of 3x. Okay, I'm going to subtract 9 times what y was, 4 cosine of 3x. We're checking to see if this is equal to 0. Okay, so let's see. So I have negative 36 cosine of 3x minus 36 cosine of 3x equals 0. Yeah, if I combine my like terms here, I'm going to get negative 72 cosine of 3x, which is not equal to 0. Okay, so this is not a solution to the differential equation because I didn't end up with 0 on the right-hand side. And don't be fooled by this. This is not an equation that you need to solve. We're just checking to see if we can manipulate the left side to match the right side. It's almost like a trig proof without actually having to use trig proofs. Okay, we're going to do the same thing for B. Hopefully B works. So B, we have y equals 2/3 x to the 3x. So again, we need all the same derivatives. Okay, so y prime is going to be equal to, so chain ruling this would be 2 e to the 3x. And y double prime will be equal to 6 e to the 3x. Okay, so plugging this into our differential equation, I'm going to have 6 e to the 3x minus 9 times 2/3 e to the 3x equals 0. Okay, so if I multiply 9 times 2/3, that's going to give me 18/3, which is equal to 6. So I'm going to have 6 e to the 3x minus 6 e to the 3x equal to 0. And look what happens. Those do combine to be 0. So 0 is equal to 0. So this is a solution to the differential equation. All right. I said this was multiple choice. It's probably more all select all that apply. So let's also check C. Okay, so for C, we're going to try the same thing. Now, you might be looking at this and saying, okay, well, we have another variable here, C. Well, C is just representing a constant. It's almost like when we were integrating and we had to put plus C, that just represented any sort of constant. Same thing here. Okay, so we're just going to keep doing our thing. We're going to derive around what this C value is. So our original function was C e to the 3x. Okay, if I derive this, C is just a constant, so when I use the chain rule, I'm going to have 3 times C e to the 3x. And when I derive it again, I'm going to have 9c e to the 3x. So plugging in my derivatives to my differential equation, I'm going to have 9c e to the 3x minus 9 times c e to the 3x equals 0. I do see here that I have a 9c e to the 3x. I'm subtracting that from a 9c e to the 3x. So my left-hand side does become 0, so 0 is equal to 0. So C is also a solution to our differential equation. Okay, let's go ahead and we're going to flip over our page. Last 2 examples. So in example 4, we're going to find what value of k, if any, y equals e to the 3x minus k e to the x is a solution to the differential equation y double prime equals 3y prime plus e to the x. So our goal at the end of this is to figure out what that constant of proportionality is that makes this differential equation be true. Okay, so again, it tells me that we're going to need to find a y double prime and a y prime, so let's go ahead and derive those. So y prime will be equal to the derivative of this. So 3e to the 3x minus k e to the x. Remember, k is just a constant. And y double prime will be equal to 9e to the 3x minus k e to the x. So let's go ahead and plug this into our equation. So y double prime is 9e to the 3x minus k e to the x. That'll be equal to 3 times what y is equal to, which is e to the 3x minus k times e to the x, and then plus e to the x. All right, so in this case, our goal is to get k by itself. Let's start going ahead and combining some like terms. So I'm going to distribute this through. So I have 9e to the 3x minus k e to the x equals 3e to the 3x minus 3k e to the x plus e to the x. Okay, so it looks like we have a couple different types of terms. We have some terms that have an e to the 3x, so those are like terms that we'll be able to combine. And we also have terms that have a k e to the x, so those will also be like terms that we'll be able to combine. Okay, so let's try to get, let's see. I feel like I'm missing something. Oh, okay, hopefully you caught it. In this place, I should have put y prime, and I only put y. So this needs a 3 as well. Great. Okay, so when I go to start combining these together, I see here that if I subtracted my 9 e to the 3x terms, those are going to go away. Okay, and then I'm going to add 3k e to the x over to the other side. Okay, so that's going to give me 2k e to the x, and on this side, I'm only left with e to the x. Okay, our goal is to get k, so in this case, I don't need any of those e to the x's, so I'm going to go ahead and I'm going to divide both sides by e to the x. So when I do that, on the left-hand side, I'm just left with 2k, and on the right-hand side, I'm left with 1. So dividing both sides by 2, I get that k, or constant of proportionality, is 1/2. Okay, last example. Example 5 says that if y is equal to 2e to the x plus y, where y is equal to 3e and x is equal to 1, which of the following is a solution to the differential equation? All right. Okay, and I do remember that there was a typo on this. This should be a 2e, so go ahead and change that. Okay, and wow, there are a lot of typos on this. This should also be a y prime. Okay, hopefully we're all on the same page. Y prime is equal to 2e to the x plus y, and then y should be equal to 2e. Okay, great. Glad we're all on the same page. So what we're going to do, since this is, again, a kind of a multiple choice question, let's just go one by one and see if this works out. So for A, it looks like we're going to need a y prime. So y is equal to e to the 2x plus e to the x. So y prime will be equal to 2e to the 2x plus e to the x. So plugging this in, let's see if this works out. I'm going to have 2e to the 2x plus e to the x, that's y prime. That's equal to 2e to the x. And then it says I'm going to add y, where y is equal to 2e. Okay, so are those the same? And the answer is no, because in this case, let's see. Oh, and x is equal to 1. Wow. Not doing well. Hopefully you're doing better than me. Okay, great. Actually, I don't want to get rid of that. Okay, so plugging in x, I'm going to have 2e squared plus e is equal to 2e plus 2e. Okay, not the same, because I can't combine these together, even though I could combine this side together. So A is not correct. Going in for B. Okay, so y prime is going to be equal to 4e to the 2x. Okay, so plugging it in, I'm going to have 4e to the first power, or to the second power. And that's going to be equal to 2e plus 2e. Okay, so in this case, when I combine this side together, that's going to give me a 4e, which is not an e squared, so again, it's not b. Going for C. Okay, slowly but surely. Taking the derivative of this will just be 2, because this has an x and this is a constant. So plugging this in, this will be 2 is equal to 2e to the first power plus 2e. Okay, again, this is going to be 4e. 4e is not equal to 2. Okay, so by process of elimination, it's d. But let's just double check why that is. So when I go to take the derivative of this, okay, y prime, I'm going to have to use a product rule here because I have an x times an e to the x. So first times the derivative of the second plus the second times the derivative of the first. Okay, so when we plug this in, I'm going to have a 2x e to the x plus 2e to the x. That's going to be equal to 2e to the x plus 2e. And then plugging in 1 for x, I'm going to have a 2e plus 2e is equal to 2e plus, hey look, 2e. So 4e will be equal to 4e. So it is d, like we thought it would be. Okay, so in summary, what we've learned in this video has been differential equations can combine together to show that there is a relationship between an original equation and the differential equation. And a solution to a differential equation is a function that satisfies it when it's all substituted in. So our goal moving forward with this is we're going to learn a couple different representations of differential equations. We're going to learn how we can use differential equations to estimate values, and then we're going to talk about some different types of differential equations that will come up a lot in context, so especially exponential differential equations and then logistic differential equations. So that's all for this video. Sorry it was kind of chaotic. I will see you all later.